Hello, everybody. So, got a few things to go over tonight. Um, Kind of continuing from last class on Monday. Uh, I consider most of these things just basic syntax of the language, but they're spread out. I think some of them are like module 3, or some of them are later in the semester. But I wanted to go ahead and look at lists. We very quickly looked at for loops, and the design of Python for loops are really intended to go with a collection. So I want to look at collections, and that's sort of a fundamental part because this can't be anybody's first programming class. So hopefully you at least know what an array and a list is. We'll look at some of the basic ones of that, talk about those, and then take that a step further and look at comprehensions and generators, because those can be more useful than just regular ones at times. Got quite a few things on here. I forgot to look at multiple assignments. Has everybody seen that before? When we assign variables, we don't have to do them one at a time. In some of our programming languages, we can only do one assignment, right? Like x equals some number. But in Python, we could say x, y, z equals 1, 2, 3, and it'll assign them to the right spot. A very, very useful thing. We forgot to look at that the other night for the basic things. Reading and writing files, I consider part of the base core level of the language. And in particular, that's going to show up a little bit later, but built into Python in the default installation are modules to read and write CSV and JSON files. More useful formats for our data. And since we were going to talk about collections, like lists and dictionaries, the JSON and CSV writers built into the language kind of flow right into that. Yeah, a few things. One thing I wanted to address first is, well, y'all are probably well aware of this, part of the reason you chose Python course. A lot of times when we're writing programs in Python, the text file we put together is a lot shorter, right? You may have even seen like various memes floating around the internet, like Reddit programmer humor page or something, making jokes about how much you have to type in a C program versus how much you have to type in Python to get the same results. And that's actually only partially true. So I wanted to take a look here at the stack. So I'm going to do it in idle. That's a nice quick way to open up the stack to address that issue. This is a software development class, and we're doing it with Python, but that doesn't mean your career plans are to only ever use Python. So I do like to kind of cross the lines, talk about generalizations and stuff. So really what the difference is, I'm going to open idle, just the basic thing that came with it. And under the debugger built in here, I'm choosing this option to automatically open the stack view. We talked about stacks briefly. We will talk about them more when we get to data structures. But a stack is how the computer processes things. It stacks up all our instructions, and then the term we use is pop. It pops the next instruction off, runs that, goes back to the stack, pops the next instruction off, pushes things on the stack, and pops them off the stack. So the computer is running a stack, and I'm just going to do a very simple example here. So like a new file, and I'm just right, our most basic one, print hello world, which everybody's familiar with that, right? Our quick check. It's really a configuration check. That particular example comes from the original Mac commercial for the original Macs. But if we can make a string show up on the screen, that means everything's configured correctly. So we don't go writing tons and tons of code and then figure out that our computer is not configured correctly. So it's sort of just the standard configuration check is what that is. But I need an error, so I'm going to like take the R out of that or something. Give that a save so I can run it. And yeah, this doesn't really need save. But if I run this now, since there's an error, it should pop open the stack. So that code I just wrote, one line, right? Not much there at all. So it seems like a very short thing. But here is all of what the computer's running. So there's two directories. So in the IDE is all of this stuff, some local and global variables. I'll just start opening some of these. In code, you can see there's lots and lots and lots of folders. Let me open up hash here. And format, that'll be an important one. And so, but layers and layers of folders filled with Python scripts and other folders scripts. Layers and layers and layers. Scroll down, you see the scroll bar is long, and I've really only expanded one of those top level things. And come over here to the main. So the first folder was the IDE, and this one is the interpreter itself. And there's even more things going on over here. So the representations, get the attributes, but you can see it. That's probably enough expanding. There are lots and lots and lots and lots of Python scripts that are running just to print the word, just to get the words "hello world" to print on the screen. So we don't put much in our file. We only do the last step. Makes it a lot easier because we just have to do that last step. The trade-off for that is in Python, we can't edit those others. We don't have any control over it. In some of our other languages, we do, which obviously makes our scripting a lot more convenient, a lot easier because we don't ever have to worry about that stuff. But there are times when we would like control over that and like to actually control how the program runs, not just the fact that it runs. We'll see some more on that soon. I just wanted to open the stack there and kind of address that issue. It looks like the Python code's shorter, but actually Python's longer. It's just we don't have any control over most of what's happening. So if we have a program that's really, really inefficient and we would like to try to get more speed out of it, we're limited with options in Python compared to, say, things in our C family, where we have direct control over that. And over the last few years, with the popularity of Python, some of the C family things, notably C# and Java, have been taking out some of that boilerplate code that is always typed exactly the same way, and we only address it if we want to change it. But ultimately, there's more than just our text file running. We'll see that quite a bit. It popped in my mind to look at it the other day, but then I remembered we have to use functions. But as soon as we get to functions, we'll look at disassemblers. That takes our Python code and breaks it down to the assembly language, so we can see what's actually running in the machine. So, like if we need to make improvements, that's pretty much our only option in Python is to check the assembly language and see what sort of improvements we can make from our script. The general rule of thumb, though, is if you're worried about efficiency and optimization, don't use Python. Python's for when you just need it to work and you're not really concerned about how long it takes, as long as it gives the right result. Anything we do in class, it's kind of hard to see that slower part. Okay? All our stuff runs in a few milliseconds, so we don't really notice it. But remember, there are some very large data sets in the world. Like if we're dealing with billions and billions and billions of items in a list, then we really start to notice that time scale. If every element in the list takes 5 milliseconds longer to go through, and we have to go through 10 billion items in that list, we're up into human time scales at that point. That's the point where we would probably want to consider using something in the C family to get back speed. But that's a different issue. I just wanted to quickly look at that. I'm jump over to Spider, because Yeah, one of the things I wanted to look at as we talk about lists and stuff was something I haven't pointed out yet, but Spider does give us a really nice variable analyzer. Gives us two analyzers: the code analyzer for refactoring, making your code look nice and matching all the conventions and all the suggestions and tips for making it look better. But there's also a variable list, so we can see all the variables and what's in them and track things that way. So I'm gonna close this. Okay, and go to an untitled one. I might as well do this. Quite a few people were using Spider. Whatever IDE you're in, there is going to be some sort of template when you start a new file, right? And we have control over that. Since I have Spider open, I might as well point at it. You go to Preferences, under Editor, and Advanced Settings. This is button for editing the template file. So, and when you do that, we can close this. This file template.py opens, and you can kind of change this. Like if you don't want to use the username on the computer, type your own name. CS, for instance, that way. Update created for SDEV 220 fall 2024, and add in whatever customization you want in the template. So that you save that template every time you open a new file, that's what you get for the starting point. Can be really, really useful. Every IDE should have that functionality. The difference is where the template is stored at. So you just look around for some sort of button that labels template, or it's usually in the preferences and the settings, but doesn't apply in Python. In Python, you can adjust whether you use tabs or spaces. The recommendation is 4 spaces, but as long as you're consistent. You can't use tab on horizontal tab on one line and then 4 spaces on another line. The indentation will look the same, but it's different internally to the machine. So you have to be consistent. So you control how that's set up, the templates. You might want to look into those things. In some of our other languages, we can control where how the curly braces start, where they lay, how the indenting is, and semicolons, and all of that stuff. You should have that functionality in every IDE. So you might want to look into that some, but there's not as much formatting we do in Python as in other languages, or the formatting matters in Python. So a couple things here. I realized after class we forgot to see multiple assignments. So maybe we have 2 variables, but we want to assign a value to. It looks kind of odd just doing it directly like this, and say A and B is 3 and 4. So that'll put them in the right spot. So like if I print B, then maybe do something A squared plus B squared. If you saw the caret for exponent, that is actually just a coincidence. A caret is the XOR operation, exclusive OR, and it is just a coincidence that if we do exclusive OR on 2 integers, we get the same thing as if we were to raise the first integer to the power of the second one. So that's kind of a shortcut, but for exponents, we should be using 2 asterisks, 2 multiply symbols. Then print C, I think everybody knows. Hopefully everybody's familiar with the Pythagorean theorem. You can see we get the second value went into the correct one here. The biggest thing about that, which is really, really useful, is if we want to switch what's in the variable. In most of our programming languages that only do single assignment, we have to do a big structure, right? So like if B is greater than A, maybe we want B to be our smaller one, we need to create a temp variable, right? So like temp equals B, B equals A, and then we do A equals B. That's what we have to do in most of our programming languages. But because of that multiple assignment, Python makes that a lot easier. We can say A comma B equals B comma A. And that's a nice shortcut to swap the values in variables. If you only have single assignment, you have to set up a structure, and then it's like the best analogy is if you have two, like little kids sometimes get very defensive, give them their own cup, like 2 and 3 year olds, and they get very, very loud, and you need to switch the cups. But you need a third cup in order to do that, right? You have to pour the contents from one into an empty cup, and you need a third cup in order to switch things. Same thing with variables. But with multiple assignments, we don't have to do the complicated one. We can just use a multiple assignment trick, and then if we print B here, it should have the other value in it. A nice, easy way to swap things in Python. Usually we wouldn't do multiple assignments like this. It's more for when we want our functions, which we'll get to next week, when we want our functions to return several values. And we write a complicated function that calculates 5 or 6 different things, and we need a place to put them all when we get them back. Where we would use that most often. I'm going to go ahead and save this randomly documents. I still have the GitHub repository locally, so I'm just going to save it here. There's multiple options. I keep showing this stuff about GitHub, but this is a Python course. So anything we do with GitHub, the web interface will work. So all this other stuff, think of as preview mode. Since you're heading into software development, I want you to be aware of all the functionality, how powerful of software Git is. But we're here to learn Python, not Git. So the Git stuff is just in preview mode, and that web interface where we can just drag our files over will work for everything in class. What is this? This is a multi-assignment.py. Try to give things good names. Before I started teaching, I used to just mash the keyboard and keep track of things by the date. But I realized very quickly in my first couple semesters teaching that really bothered some people. Like, that's an awful name. I can see them cringe every time I save a file by just smashing the keyboard. So multiple assignment, that's a very useful thing. It'll be even more useful when we get to functions, especially when we get to callbacks and a couple other things about functions. Swap variables, got that. Look at the stack. So I want to talk about collections a little bit. In your previous classes, should have seen at least a little bit about arrays and lists, right? Everybody see those in previous classes? There's some technical distinctions. We don't have arrays in Python. Should I write it on the board? Probably could have pulled up my notes beforehand, but I don't see when I look quickly, but I'll go ahead and write the definition on the board. So an array for the software development part, we don't have arrays in Python, is a collection of similar typed data stored via a recursive algorithm. So in those pictures that I'll be using a lot this semester, so like a stack heap diagram, the stack is our code and the heap is RAM. Does anybody have any trouble seeing colors? Are there any markers I should throw away? I should check that before I start color coding things. Okay. I always like to check that and make sure. I've heard, the big one I've heard is for people that have trouble seeing blue. I might as well be writing with a white marker on the whiteboard. So I don't want to be writing notes up
That's
here.
the only one. Yeah, Professor, the only one that I can't see is green very well.
Oh, you can't see green? Okay.
Yeah.
I will get rid of my green marker right now. So black, red, and blue. That'd be enough color coding for us. I might try to grab a fourth color, but I think, yeah, a couple colors will be enough. I'll do arrays in blue. So we created an array, not in Python. Does anybody see the problem with the definition as far as Python goes? What words in that definition just don't fit with Python?
Data.
Mm-hmm. Or in particular, the type data, right? Python's dynamically typed, so we do not have similar typed data. Or data, however you want to pronounce the word. If you haven't heard before, it is a Latin word, so and we use it the same way the Latins did, or the Romans did. So data would be the pronunciation, whereas data was a popular character in Star Trek, but just so happened to be a popular character at a time when that word was becoming part of the English language. So if anybody ever asks you that question, both pronunciations are acceptable. Because also database sounds weird. If we're going to use a bunch of different, pronounce a different ways. So collection of similar type data. So we have a bunch of things. So this will point at the first one. I'm going to draw it like 8-bit integers, right? So 1, 2, 3, 4, 5, 6, 7. So we have 8 bits somewhere in RAM that hold the first number. And then a recursive algorithm might be something like start plus 2 times the size of our data plus 16. Just some sort of algorithm like that. So start, maybe the computer checks RAM and sees, okay, bit number 100 is open. So there's room around that, so we can start there and just shove the data in bit number 100. So we have 100 plus 2 times size. We have 8-bit data. So 16 plus 16. And our next one's going to be at 132. So after that, I don't know, I'll draw it over here. The second one's look, bit number 132 in RAM. So then we start at 132 plus 2 times 16, or 2 times 8 is 16 still, so plus 16. And we get the next one's at 164. Makes sense how that recursive algorithms, but we just keep feeding it, keep using the same formula over and over again. This is kind of an old one back in the early days of computers where we actually had heating coils melting, heating coils flipping mercury switches. Turning on 2 bits of RAM next to each other was kind of a fire risk. So we would spread the data out. Nowadays, the algorithm is usually like +1 or plus size, right? If we had 8-bit integers, our recursive algorithm would be +8, and we just use the next 8 bits in RAM because it's not a fire risk anymore. But I exaggerated it for the picture there. So then our third one is at bit number 164, and that's how the computer knows how to find those. And we ask for them. This is where the indexing comes from. When we ask for something, we need to start here, right? We need to start at the beginning before we get that first bit. So that's why we ask for index 0. So go to the start point plus 0. But I'll put it here. We ask for the beginning, but we don't count that until we get to the end, because we need all 8 bits before we know what number is in that spot, right? If we use 8-bit integer. There was a question showing up beforehand. It wasn't exactly clear in the book. It said integers can be 32 or 64 bits. And that has to do, Python will try to use 32-bit integers, but there's an upper limit to that. Okay, let's put it in Google. What is the biggest 32-bit integer? Oh, that did non-negative, so cut that in half. So 2 32-bit signed integer. There we go. Oh, I remembered a 2 and a 7, but I was a little off. It's 2,147,000,000. So this number is the largest one we can fit in a 32-bit integer. So Python will go with that. But if we tried to turn around and store 2,147,483,648, that's no longer going to fit in a 32-bit integer, right? But we don't get one more bit for the next size. As soon as we pass that number, so the 648, we jump from a 32-bit integer to a 64-bit integer. Those are the two sizes. And if it gets too big for a 64-bit integer, this question showed up and yeah, it wasn't the clearest thing. A much bigger number, but it's still finite, right? If we pass that, it goes into another process that we usually refer to as big integers or big floats, where we store it as a string, and then we calculate the value of each position as it's needed. But it's stored as a string. That's how things like pi to a trillion digits get stored as big floats. So it's a string, and then we calculate each one of those digits as we need it. That's what those sizes mean. And we can't have a 33-bit integer if we have something that's just a little bit bigger than fits in 32 bits. But I didn't really want to draw 32 slots on the board here, so for our picture, I'm going to use an 8-bit integer. And this is how it knows where it's at. So ask for the array plus 0 goes to the start point of the first one. But then we don't count the start point of the first one until we get all 8 bits in. So then when we want the second one, we do start plus 1, which takes 8 bits over, gets to the end there, and then it's going to jump through the algorithm to the next one. So here's start point plus 1, jumps over here. Then start point plus 2, the second element ends here, which jumps us up to the third, where the third one's stored. That's what an array is. We don't actually have those in Python. Very, very fast, because the computer doesn't have to do any extra work to figure out where they are. I was doing that like it was in order, but the computer would just automatically do the calculation and jump to that spot in RAM. So a very, very fast one. We also have lists, which are typically in introductory things. We use the word array because list means something to most people. We use that all the time, right? You've probably dealt with a list in your daily life at least once by this point today. 6 o'clock in the evening, surely you've done something on a list by now. But not the same thing as a list as far as the data structure. So a list is collection of data or data organized or stored. Yeah, the technical definition has a bunch of extra words that are stored in RAM and organized by pointers to other elements. So notice there's no restriction of similar type of data here. We can put it in a list. We can throw in some integers, some strings, some booleans, mix and match whatever type we want. They don't all have to be the same thing. And instead of some algorithm that we have to do calculation, that's why we have to have a specific size for an array, because we're gonna do calculations, we just have a pointer going to the next one. So if we have a list, I'm gonna call it LIS to kind of match that. We'd have the first one wherever it starts. The computer's gonna remember where that's starting. I'm gonna skip the numbers this time because we're not doing a calculation. Our variable from our code points there at the start. And instead of a fancy algorithm to get to the next one, we just add a little bit of data at the end. We add a little bit extra at the end that says the next element's over here. Store the second one there. And then indexing is the same. The start plus 0 gets us to here. We start reading in those bits. And then over at this point is where we get to the one element in. So that's where that difference between indexing and between index numbers and linked numbers comes into play. Again, we add another one here, and we're gonna make a list. When we get to data structures, we're gonna make our own list to make a stack out of. And this is just a when we do make the object, we'll just add an extra data field in there, or a variable, attribute, whatever word you want to use. We'll talk about object-oriented stuff soon. We just add another one in there called next. And then what's stored in that next variable is the next element in the list. And then it gets a variable called next. And what's stored there is just the next element in the list. So it's a bunch of things pointing at a bunch of pointers to the next elements. And eventually there's a pointer that doesn't go to anything. I'm gonna draw the electrical ground symbol, the null pointer. You may have encountered null pointer exceptions. If we hit null pointers by accident, that's a problem. But if we know it's there, then we just watch for it, and it's a great way to, in this case, mark the end of the list. When we hit that pointer that just that the electricity just flows back to ground because there's nothing there and we're not keeping track of the data anymore, that's how we know we're at the end of the list, and it doesn't take any processing power to find that. Null pointers are a big problem if we hit them accidentally. But if we know they're there and are watching for them, it's a pure electrical thing, and it doesn't take any processing power to find it. Lists are also dynamic, right? If we wanted a bigger array, well, everything here is calculated beforehand. So we need to, if we wanted a bigger array, there's 3 elements there, we'd have to create a new array that had 4 elements in there and then copy all of these 3 over to it. Because it's all determined beforehand. But a list, if we wanted to add another thing instead of this null pointer here, I'll do it in black. The edit, we can come in and dynamically edit the list. So instead of the null pointer here, we'll just point at another element down here. And our list has gotten longer. So we can add things to a list. Or if we decide we don't want this thing anymore, all we have to do is stop pointing at it. So in our object making up the list, this is a data field or an attribute or a property in there. A lot of people just think the word variable because it makes sense from how we all start learning our code. We just take this variable that's holding this element and have it hold this element instead. We just point at something different. Now there's no way to access this element. So garbage collection will grab that on its next pass, which is one of the things that really made Python stand out. Python has some of the nicest garbage collection out there. We will see how to kind of get in there and mess with it. We'll see a couple things, but Python has some of the nicest garbage collection going on in the background. So we never have to think about that. So we can take things out of a list just by pointing to something else. We can add new things to the list just by adding stuff to that null pointer at the end. So lists are very, very dynamic. That's our basic structure in Python. Also, does the stack heap diagram make sense? We're going to use those a lot when we get to data structures and talk about the differences. That'll make a difference. Not anything we do in the classroom, but when you have like real world size data sets, lots and lots of things where you start to notice the time difference on human time scales. Little things can buy you back quite a bit of time. But all in all, we'll just kind of talk about that stuff a little bit because that's what computer science is. Computer science worries about optimizations and refinements and getting software to run as good as it can possibly run. Whereas software development and software engineering is just looking to get the software to run. If it runs and gives the right result, that's good enough. Computer scientists worry about trying to perfect it, which gets very, very stressful at times. If you were curious about the difference between those. So a list, I'll just make something on my list. Everybody's seen the syntax before. We use square brackets. Spider won't say zoomed in. Let me zoom in a little bit so it's bigger there. We use square brackets and then we can add some things in there. So like 1, 2, hello world, true, 3.14. Mix and match our data types. So we have a couple of integers, string, a boolean, and a floating point number all in there. We haven't got to our own custom data types yet. And then we can access them from indexing. I assume everybody has seen this before, right? So if I ask for index number 2, what's going to print? Somebody want to tell me?
Third one.
Mm-hmm. Yes. That discrepancy, because the start plus 0 gets us the first element. The start plus 1 gets us the second element. And yeah, so we should see hello world. Zoom buttons are in my way. Maybe it'll be out of the way here. Maybe it'll be out of the way there. Yeah, so print hello world. If we want to extend the list, my list dot append will allow us to add a single element on. So let's add a 5 there at the end. A 5 and a 2.82. Couple good numbers. So now if we print my list, I'll just print the whole thing out. I'm going a little quicker here because I assume everybody's seen this before. List.append takes exactly 1 argument and 2 arguments were given. So it didn't like adding 2 things. If we want to add 2 things, I'll show that here in a second. Yeah, again, I like to show errors in class because being able to make sense of the error message, right? It takes exactly 1 argument and gave it two arguments. That's a pretty clear message. Like put too many things in the parentheses. Do that with just 1 argument. We can see that added to the list. If we want to add a couple things, we can use extend. My list.extend, and then we extend by another list. So here maybe 7 and then 2.82. And then false. Just a, let me add some spaces in here with it a little bit easier to read. So you can see if we have another list, maybe it's stored in another very useful variable name somewhere else or typed directly in like this. But we can extend a list with another list. Print my list and make it a lot longer. Maybe we want to change what the second element is, or the third element, right? We printed the third element earlier. That's where insert comes in handy. So if we do, actually, whoops, I'm going to hit end and hold shift and hit the home key. That's a really useful way to highlight a whole line if you haven't seen it. Before the days of the mouse, we would use the shift key to highlight things. I'm just adding some white space there because I don't like typing at the bottom of the screen. And the Zoom thumbnails are at the bottom of my screen, so I can't see the bottom of the screen anyway. So that was just for scrolling. But before the days of the mouse, we would use the shift key to highlight. So if you hold shift and say the arrows, it moves back and forth. Shift control arrows move word by word or break by break. It will try to figure out where the next best logical place to be is. But what I like to do is just click anywhere in the line, then hit the N key and hold shift and hit home, because highlighting a whole line is something we do a lot with that, if you haven't seen that shortcut before. And that completely distracted me from what I was just getting ready to do. Oh, insert. So maybe we want to change what the third element is. So we also have insert, and you can see on the predictive text, index. What index are we changing, and what are we putting there? So maybe I want to change index number 2 to say new thing, and then print that out. Print my list. I haven't saved this yet, have I? Probably save. That's always a good habit. What's this? Collections. So we're gonna have quite a few. So run that, and you can see that puts it in the middle. That is especially useful, right? All the work we're doing here right now, or in my example, yours is gonna be slightly different, but I'm in this folder doing stuff here. But if there was a new folder here, I just need to create it. Maybe I have a module I want over in a new folder, and I want to import that into a script into this collection script. That could be a bit of a problem, right? Because if they're in the same file, we can just use it, use the name. We don't. But if it's if we have to go like up a folder, or maybe not there, maybe we go up a folder, and the module I want is in this new folder. Right? That's a little bit harder to get to. Or up and down. Relative addressing, we can go up and down, but that's outside of the repository. So we have to look someplace else for that entirely. That's kind of what I was going for. Something that's not easily where we can just use the same name, or not really quick with relative addressing. We might have to put the entire file path to it. So where those are stored is if we import the sys module for system. Let me print this real quick. Print sys.path. This last thing that's going to pop up here. This is where Python, you'll notice there's a list there of a bunch of file paths. This is where Python looks for other modules. You see a whole bunch of them around the computer. Down here is the empty one, so it's not even looking in the same folder until it's looked a whole bunch of other places trying to find it. But I know exactly where that is. So that insert I find really useful. So then I can do sys.path.insert. No, I want to look from the current location up a directory and then into new folder. The name there. So I know I want to insert that in the path from wherever this runs. And now if I, I'll just copy this line. Actually, I'll cut that line because we don't need to see it twice. We already saw what it is. Notice what the first one is. And insert takes that index. So if I know that I want to look in this particular folder every time, I'll just insert that at the beginning of the list. Because there's no need to have Python look all of these other places on the computer when I know where that module is. So you can see now, first place it's going to look for other folders is just go up one directory and into that next folder over. That happens a lot as our projects get big and we start organizing things into lots of folders. You might have to go up and down several folders, and then you can just put that in one of your things, and then you don't need to worry about putting an entire file path because Python already looks there for the module. That's list. Quick version of list. I'll add a comment in here. This. Whenever I do make comments, I usually put extra symbols. People often question about this. I've heard people ask enough times. One comment symbol is enough, but it's also easy to accidentally erase one comment symbol, and then you get errors. So over the years, I've just learned that it's kind of nice to have extra comment symbols in there because worst, best case, they just stay commented out forever. But if you were to accidentally delete one of those symbols as you're editing things, you don't end up with the you don't end up losing your comment. Tuples are just like lists. Lists are dynamic is the main thing, and a tuple is static. Has everybody seen lists and tuples before? Just like a list, except cannot change. So all of the stuff is the same, except how we use parentheses. 1, 2, 3. Hello. False. 3.14. So we store the stuff just the same and we can index it. So like my tuple print my tuple index 3. As well print out the words that are there. You see, we still get that printed thing. I'm going to call it this. Whoops, that's not it. I just have to. Oh, no, that's not it. Maybe it's control 1. Control 1, if you're using Spider, comments things out. Usually control / is the comment to section out, but that can be changed. That way we don't end up with that big useless. So we can still print that out, but if we try to change it, right? Say my tuple index 3 is going to be a world instead of hello, so it's going to crash. So you don't even need to print it. Tuple does not support item assignment, so we can't put something in there like it's variable. This tuple dot append. Whoops, I can spell it correctly. Predictive text noticed it. Let's put world there this way. And tuple object does not. Tuple object has no attribute append. So a tuple is non-dynamic. A couple advantages is kind of like that thing I said with arrays. If we want a different tuple, we have to make a new tuple, copy everything over, and then add the new stuff to the new one. We have to make a new one that has all of this stuff, plus space for more things to go in. Some advantages of that are obviously it's going to take less RAM. If it can't be changed, we don't need to reserve RAM for situations where we might change it. So it's better on the resources if you know your data is not going to change. For example, if you read a bunch of stuff from the database, process it in your script, and then delete it from RAM when you're done, it's not going to change while your software is running. So you can use the resources more effectively by using a data structure that does not change or does not allow for change, because to be ready to change things requires computer resources, which translate into time eventually. We haven't looked at variables yet. Let me run this again in a way that doesn't crash. There we go. If you're using Spider or any IPython console, Control L is clear. That comes from IPython. See this tab here, Variable Explorer? If you don't see that under View, is the Windows somewhere. Yeah, window. No. Maybe it's not under View. Oh, under View and Panes, here's all the different options and things you can turn on and off. I'm turning off the help menu. This one's useful, if I can remember it. If I put my cursor on print, is it Control I? Yeah. So put your cursor anywhere in the Python code in Spider, and Control I will pull up the documentation. Or how the other day we kept going to Google and looking at the official documentation. This will pull it up. And that includes documentation that you put in your own code. So all of We don't have functions yet, but once we make a function, if we document that, the help menu will pull up our own documentation as well. It's a dynamic help menu. But that can be a little bit quicker than going to Google if you're gonna follow that tip I gave and always check official documentation first. So yeah, there's the user manual on the print method. That can be really, really useful. And again, under view and panes, we can turn all those on and off if you're using this. Don't need to help menu. History can be nice. History's down here. Here's all the stuff we've ran. So even though it's notice it's not necessarily the outputs, it's the I was expecting some lines. I probably have it set to 50 or something. I don't know what the default is, but it's showing the last 50 commands that have ran through that console. That can be useful at times. Also, variable explorer. This is kind of useful because notice says what we have, integer, the size of it, what's stored in there. My list has all the elements stored in there, the tuple, we can see what's stored in there, and it gives us a way to see what the variables were, which is really, really useful when we use, say, that blue button. Maybe click on number 17 here, or see how that red dot to bring in the like a debugger. Why is it not giving me a breakpoint? Oh, maybe I have to do this. Okay, it has to be a line with code in it. On line 18, I'll click right beside the number, and then I can use the debugger one and run step by step. So it runs up until line 18, and then it pauses. We can see everything that's going on, see what the variables are doing at this point, and then do the step by step, or jump all the way to the end if we figure out what it is. Run the current line, go into a function, or run until we hit the next function call. You'll want to play around with the debugger. Any IDE, any of your IDEs should have some sort of debugger, or there are also external debuggers that you can connect things to. But we can just run line by line and then check what the variables are at each point and use that to track down problems. I see we're ready to create this line, so when we run that, whoops, I hit the wrong thing. Oh, I started over. We'll try that again. Go down there, and whenever we run that line, then we see the variables changing as we're getting to them. The blue buttons are the debugger, and the green buttons are the regular runs. So this is yeah, and apparently it lets me run more than one debugger thing. I didn't realize that. I accidentally hit the debug button twice, and after that second one stopped, it went back to the first one. I've never done that before. I never really checked, but apparently Spider lets you have multiple versions running at the same time. And then I'll just click again on that red dot to take out the breakpoint. Debuggers are useful. Make sure you know how to use those in IDEs. I mentioned a couple times at this level, it's good to check different IDEs, see which ones you like. There are also external debuggers. So if you like the super simplistic version, that's generally what I like. I'll use simple text editors and then like external debuggers, which often have more functionality than the built-in debuggers. But whatever IDE you're using, make sure you're comfortable with the debugger. On simple problems, you want to learn to use the debugger on something simple that you could debug just by looking at it, and then understand that tool, so that whenever you get to something really, really complicated where you actually need a debugger, you know what to do on it. Couple other basic ones. Oh, for loops are really intended to go with things like this. Right? You probably saw we introduced the for loop with the range function. That wasn't, first time I used Python was 2006, and I was using Python for 10 years before that was added in. So that is a fairly new, that range, for I in range, that is actually a fairly new addition to Python. For loop is what we, in most of our languages, we call for each. So really that, if we read it that way, so like for each, what do we have? Item in my list. And now we can just print item, and that gives us a way to refer each item. We rename each one of those things. So it'll just loop through that whole list. And that's something we do a lot, right? We look through the whole list and it prints them out one at a time. No surprises there. I assume everybody's seen that before. It's collection. So if we read a file, for line in file handler, it's going to, Python is going to try to find the natural splitting spot. So on a list or tuple, it's obviously the elements. In a text file, it's the lines in the file. But what it'll try to split it up in the natural way it splits up. And a lot of times, this is what we want right here. We want to go through the whole list, right? We don't want to look for a particular element in the list. We want that whole list every time. When that's what we want, a set can be really, really useful. Sets. No indexing, no order, just the whole list every time. So if we're going to go through that whole list every time, we don't need to waste spots in RAM with those index numbers or keys, because we're going to look at a dictionary next. Those are even bigger than indexes. The trade-off is that the computer will dynamically choose the order of the elements. So we can't guarantee that we're going to get the same order every time. But if we just want everything in the list, right? Like on payroll calculator, we want to calculate the payroll for all of our employees. We don't want to pick and choose which employees get a paycheck and which ones don't. So we're going to, and we really don't care which order it gets calculated in. Right? Maybe Bob's paycheck is calculated first this week, and Sally's paycheck is calculated first next week. Doesn't make any difference. They both get their paychecks on payday. Their direct deposits they get their direct deposits at the same time. So we don't care what order it calculates in, but we do want the entire list every time. So sets take out a lot of the overhead, kind of conserve some RAM. My set, and it's a lot like a list, except we will use curly braces this time instead of square brackets or parentheses. 5 for true words, random stuff, whatever's in that list. Whoops, I forgot to turn my phone down. Sorry about that. So inside of the special characters, it looks just like we saw with lists and tuples. And we use the curly braces to indicate it's a set, which means the order doesn't matter. We don't have any way to index it. So like print my set, if we tried index number 2, set's not, there's no way to refer to a particular one. That's for when we want the whole list every time. So either printing the whole thing out or iterating through for S in my set. Print S. And kind of going quick tonight because sets weren't on the list, but list and dictionaries, the next one we're going to see, are in module 3. So we are looking a little bit ahead, but I kind of expect that most people have seen this a little bit before. Almost everybody said they'd seen some Python before when we asked. So this is when we want to use a set. If we're going to use the whole set, the whole collection every time, and we're never going to single out any particular thing, sets are a lot more memory efficient. You can see the loops and stuff are the same. We can't index it. my set dot append. What do you think? Can we add stuff to it? You want to take a guess? We can check, right? It's really easy to just hit the run button and check if we can do that or not. No, we can't add stuff to it. It is fairly fixed. Can't extend stuff. So in that sense, it's like tuples. If we meant to put what I put there, 5 things, if we actually meant to put 6 things in there, we need to create another set and copy these 5 things over, and then put the 6th element in there, which also kind of gives us a layer of protection for our data, right? We can't accidentally mess up our data. That's probably the place where tuples are used most often, is for that non-dynamic part. We can't change it, which means we can't accidentally change it. It prevents that. It helps prevent accidents. Is one of the big uses for those. Sets have a similar thing, and it's no indexing, no order to it. For our example here, we're probably getting the same order every time. 1, 2, 3, 4, 5. Well, you can see right there. When I printed the whole thing out, true words 4, 5, random stuff is not the order I put it in it. The for loop did the same thing. This one's small, so it kind of went through in the same order. But the order it printed is not the same order I put it in it. And on much larger sets, it could be different every run. Like those 2 things, print the whole list or loop through and print the whole list, could give us 2 different orders for it, because the Python interpreter is determining the order.
Is that what Brandon does?
Randint does as a complicated.
Okay.
Well, Randint is just a random number generator, so it uses probabilities. It runs through some, like that TV show you were watching. Oh, I did figure out what that number was.
Oh.
Sorry, this is a little sidetrack. I'm easily distracted. That's part of the reason we started out slow in lectures. It was for a poker hand. So the number of possible combinations divided by 5, because there's 5 players. And that's where that number came from.
Okay.
I'm a math person. It was an episode of Numbers, right? Yeah, they gave a strange number for the possible combinations in poker that she thought was way too low. So she asked me about it, and I was like, "That's low." I ran some calculations and told her what the actual numbers were, and it's like, I'm not sure what that was. Maybe it was just for Hollywood, but in a poker game, it's not just the combinations, because we have 6 players. So we take all the combinations and divide it out 6 ways. Sorry, that was a complete distraction answering the question from like Christmas break that I didn't know the answer at the time. That's why I like to start off slow, so y'all can kind of get used to the way I am when I give lectures before we get into the in-depth stuff. I'm very easily distracted. One more of these though, dictionaries. For those who have had C family stuff, we do not have mappings. Normally, dictionary is a subset of a map, where our key is a string. That's what almost all our maps are. If anybody knows those words I'm saying. But up here on this index, right? When we did some indexing, we had to try to remember which one index number 2 was, or which one index 7 was, and it's not a very useful way to keep track of our data, right? So a more useful way is key value pairs instead of indexes. And for those who have had any experience with the C family languages, there a dictionary is a subset of a map, which we're not going to dig into right now because we're not in C family class. But in Python, a dictionary is parallel arrays. It sets up 2 arrays. One of them has keys and one of them has values. Key value pairs instead of indices. I'm not sure which one of those words is right. I'll leave the X in there. This isn't an English class, but I'm pretty sure the X is wrong there. Oh, indices has an extra I in it. I remember how to spell it. Sorry, distraction again. So a dictionary is a lot like, it looks like a set. We use the curly braces. So I'll abbreviate it because dictionary is a long word. My dictionary, because I want to abbreviate that. And we index it by a string, a useful string. So like age, I'll use my age, 45. Yeah, I'm up with age. I saw a couple people in the internet discussion board talk about weightlifting. And I just had to lower my weight thing because I'm closer to 50 than 40. So I got to start. I'm at the point I got to start worrying about aging. So my weightlifting's going the other way. I just decreased it instead of going up. But getting sidetracked again. Age, and different things like that. Name. I'll put my name in there. So it's just like a list. We have different things. I have a couple goldfish at the house that have been around for years. I did not know goldfish lived like 20 years. It has surprised me. Actually, I went to Feeder Supply and asked for the feeders fish because they were just so much cheaper. And I just needed them for a hydroponic garden. And that was in 2008. I only have 2 left, but I did not know that goldfish lived that long. I thought they were like very short-lived things. And then to index it, print, we'll ask for the name of the collection. And then instead of a numerical index, we use that key. It's just more useful to keep track of things. Makes it a lot easier to keep track of what our data is. It also works very, very nicely with one of our standards for transferring data across the network. We will see that soon. If we want to add stuff, we can't do append or extend. We can extend with another dictionary, but I'll leave that for you to look up. But my dictionary, if we want to add stuff, we have to add another key in. My dictionary car is going to be assigned G Patriot. I obviously use some of my own data there. And now I'll print the whole thing out. So another way of doing collections, that's our basic collections. To see how we have those key and value pairs. So instead of numerical indexes, which are really hard to keep track of, we use a nice useful word. It makes our code look so much cleaner. It's great if you're on a team, because then if somebody else writes the key, if you're reading over one of your teammates' code, you don't have to try to figure out what the index is. You don't have to try to figure out what index number 4 is. You can usually tell from the descriptive key. And we can loop through those all the same. Those are kind of set up those loops, right? So for E in my dictionary, I'll just print them. Probably do something more interesting than print them when not in just a simple classroom example, but notice what it prints. It printed the keys. So we might want ways to access the keys or the values. I'll do this. E dot. I was expecting to. We have a bunch of things here. Find form is all sorts of stuff showing up here. Well, I'm going to go through the other process. This is what you're going to do when you're working on homework, right? So the for loop gives us the keys, which kind of tells us what to do with it, right? by dictionary D. So in a for loop, we would feed that in order to get the values. There's a way to get the keys. If we know the value, so like I know 45's in there. So print D dot value 45. I think this is the one I want. Nope, that's not it. This is the process you all are going to go through, right? So, no, it wasn't my first guess. I would generally recommend 3 guesses. Don't waste a lot of time, but you're going to understand things better if you take a couple guesses based off what you already know about Python. Take a couple guesses. I wouldn't waste a lot of time. I usually say 3. If I don't get it in 3 guesses, then go look it up. Right? How to get dictionary key in Python from a known value. Convert the keys and values in the list. Find the matching item from the list. Use the index to find the appropriate key from the list. So it's kind of a long roundabout way. Most of our languages, when we have key value pairs, there's a shortcut to get the other one. We don't really have that shortcut. So kind of what we did here. The for loop automatically does it. Well, we did a multi-part for loop, right? Has everybody seen those? I'll do it with the range function. For I and j in enumerate. Oh, well, enumerate my list. That'll work. Print I plus, I guess I better ask that as a string. Print I plus dash dash, maybe some spaces, some dashes to separate it, plus cast j as a string because my list had a whole bunch of different things. But notice when we do this, we get the indexes and the values in the list. So it brings up a question. Last thing before we take a break, this is what you'll want to do some of this while you're learning. What if we try to do 2 things in a list this way? What's going to happen? Okay. And the worst that's going to happen is the program's going to stop running and spit out an error message, right? So it doesn't hurt to check these things. Let's say print cast as a string k plus some sort of divider plus cast into a string b. No, that didn't work. So I guess this was kind of the intention. This is what we have to work with. If we put it in a loop, we get the keys. And it gets a little more complicated to try to get keys and values and separate them back out. But I just wanted to go through that process, right? Trying things. Try random things, right? You see a little bit and it's like, I wonder if this works. Give it a try because this right here is the worst that's going to happen. We'll spit out a message. And in Python 3.10, they cleaned up the error messages a little bit and everybody loved it. Even people that have been using Python for years and years and years. So in 3.11 and then 3.12, they improved error messages even more. And they'll probably continue next year after some user feedback, improving error messages. Quite a bit of things we looked at there, right? We've got all of our elements here. Notice this though, in that print. The last one it printed is showing the key. But the last one that printed is the value. Never mind. I was going on something. a little change there, but we don't need to dig through that. Variable Explorer, a lot of IDEs have those, so you'll want to check and see if your variable, if your IDE has one. Very, very useful. A bunch of collections will use those. Those are some basic ones, and we will extend those with data structures. And right after a break, the two we're going to use, one we're going to use most often is a list, right? But there's a couple things we can do better with the list when we get comprehensions and generators. Now it's probably a good time for 10 minutes. Does that sound good? I know I'm getting very thirsty. I had some coffee in the office. But yeah, I've been talking for a minute. I'm going for you. That's it. Does anybody have any questions before we take a break? That sounds good to everybody. Okay. I see head nods in here. So my laptop says 7:17. We will get back to it at 7:27 with list comprehensions and generators.